So let's take a look at Stokes Theorem. So let's say we have a surface S, which is in black, and then we have a line C, which sort of surrounds the surface S. Now what Stokes Theorem does is it relates the surface integral over a surface S to the line integral C, which surrounds the boundaries of S, the surface. And so the formula for Stokes Theorem is going to be the line integral along C of the dot product of the vector field f and dr is going to be equal to the surface integral, or the double integral described by the surface S, of the dot product of the curl of f and ds. Now the good thing about Stokes Theorem is you can use either formula. So you can either use a line integral formula or the surface integral formula, just depending on the problem. And so when you're asked to evaluate the double integral described by the surface, you're most likely going to use the line integral formula. And when you're asked to evaluate the single line integral, then you're most likely going to have to use the double or the surface integral formula. Now remember, in order to evaluate this line integral, you're going to have to rewrite it as the integral from a to b of the dot product of f of r of t and r prime of t dt. So you need two things. You need the vector field f, and you also need a vector function r of t. Now keep in mind, it doesn't always have to be r of t. It could also be r of theta or something like that, just depending on the problem. Now in order to evaluate using this formula on the right hand side, you can treat it the same way as we were to evaluate the flux of f across S formula. So basically the flux integral, or the double integral described by the region S of the dot product of f and ds. But instead of f, notice we have the curl of f this time. So we're going to first find the curl of f. And so the curl of f, since it's a cross product between del and f, it's going to give us another vector. And so that curl of f will be equal to p times I plus q times j plus r times k. Similar to how f was equal to the exact same thing. But instead of f, this time we're going to calculate the curl of f first. Then we can go ahead and use the formula, where if we are also given a function z in terms of x and y, we can go ahead and use the formula double integral described by the region D of negative p times the partial derivative of z with respect to x minus q times the partial derivative of z with respect to y, and then plus r times dA. So once again, remember, same exact formula as the flux integral, but instead of finding f, we have to find the curl of f first. Then we can go ahead and evaluate like the flux integral. So for this next problem, let's go ahead and use Stokes Theorem to evaluate the double integral described by the surface S of the dot product of the curl of f and ds. So for number one, we have f of xyz equals x squared e to the yz times I plus y squared e to the xz times j plus z squared times e to the xy times k. And then S is going to be the hemisphere, x squared plus y squared plus z squared equals 4, where z is greater than 0 and it's oriented upward. Now talking about orientation, remember that upward orientation or counterclockwise orientation means positive orientation, while clockwise orientation and downward orientation means negative orientation. And remember, the only difference between positive and negative orientation is when we have negative, we just multiply the integral by -1. Now I believe all the problems we do in this video are going to be upward orientation or positive, so we don't have to worry about multiplying by -1. But just make sure that when it's a negative, you do multiply by the -1. Now second thing here, realize that since it's asking us to evaluate the double integral, or the surface integral, we're going to have to use the other formula, where we have the single integral, or the line integral along C of the dot product of f and dr. So remember, in order to evaluate using this formula, we have to change it to the integral from a to b of f of r of t and the dot product with r prime of t dt. So once again, we need to have a vector field, which we already have, and we need to have a vector function r of t. Now in order to find a vector function r of t, we need to look at the surface that's given to us. In this case, it's the hemisphere, x squared plus y squared plus z squared equals 4, and that z is greater than or equal to 0. So if I go ahead and graph this surface, notice it's a hemisphere, so we're basically looking for a half sphere that's going to sit on the positive z-axis right on top of the xy plane. So this is going to be the xy plane. We have the z-axis on top. So we're basically looking at the hemisphere here. Looks something like this. Now since rho squared is going to be 4, then rho, or the all-around radius of the hemisphere, is going to be 2. Let's go ahead and call that rho equals 2, or the radius equals 2. Now the vector function we're not going to get from entirely the hemisphere itself, but what we really have to find out is what is the projection of this hemisphere surface onto the flat xy plane. So in other words, we're going to be right on top of the hemisphere and we're going to look straight down on it. What will we see? Well, we're basically going to see the base of the hemisphere. In other words, a circle with its center at the origin on the flat xy plane and a radius, same radius as the hemisphere of 2. So now this is how we can come up with a vector function, r of t. So remember that x, for a circle, x is going to equal r cosine t, or r cosine theta. Let's go ahead and put it in terms of t this time. So the radius is 2, so we have 2 times cosine t. Y is going to equal r sine t, or in this case 2 times sine of t. And then since there is no z-axis, we're just looking at the flat xy plane, z is going to equal 0. So if we put it in a vector function, r of t is going to be in component form. Let's just go ahead and put the x component first, so 2 cosine t, comma the y component, 2 sine t, comma the z component, 0. And since this is a circle, the t-bounds go from 0 to 2 pi. Just treat it like a unit circle. Obviously, a unit circle will go from 0 to 2 pi, so the t-bounds go from 0 to 2 pi as well. Now notice in the formula we need r of t and we also need r prime of t. So let's go ahead and take the derivative of the vector function. So r prime of t equals derivative of 2 cosine t is going to be negative 2 sine t. Derivative of 2 sine t is going to be 2 times cosine t. Derivative of 0 is obviously going to be 0. So now we can go ahead and find what f of r of t is. So we're going to take the components of r of t. Once again, 2 cosine t is the x component, 2 sine is the y component, z is going to be, or 0 is going to be the z component, and we're going to go ahead and plug it into the vector field. So we have x squared, so that's going to be 2 cosine t squared, or 4 cosine squared t. We have times e to the y times z, so we have e to the 2 sine t times 0, that's just going to be 0, plus, or times I, and then plus y squared, so that's going to be 2 sine t squared, or 4 sine squared t, times e to the x times z. So 2 cosine t times 0 is 0, so we just have e to the 0, times j, and then we have plus, now z squared is 0 is z, so then z squared would be still 0, times e to the x times y, so we have 2 cosine t times 2 sine t, that's going to be 4 cosine t sine t, but that doesn't matter because 0 will just cancel it out. Then we have times k, but that also, remember, that won't cancel because we have 0 as our z component. So what we have left is 4 cosine squared t, e to the 0 is 1, times I, plus 4 sine squared t, e to the 0 is also 1 once again, times j. So once again, that is going to be equal to f of r of t. So now we need to go ahead and take the dot product of f of r of t and r prime of t. So there's r prime of t, here's f of r of t, let's go ahead and take the dot product. So the dot product, once again, we're going to multiply similar components. So we're going to multiply the x components first. So we get negative 2 times 4 is negative 8, cosine squared of t, and then sine of t. And then we have plus, we're going to multiply the y components together. So 4 sine squared t times 2 cosine t is going to be 8 sine squared t cosine of t. And then we can multiply the z components. Notice the z component for f of r of t is 0. The z component for r prime is also 0, so we can just leave that out of the way and cross that out. Now what I'm going to do next is go ahead and factor out a 8. So we get 8 times, and I'll rearrange the two terms. So I'll put sine squared cosine t first. So we have sine squared t cosine t. Since there's a negative, I'll move that next. So then minus cosine squared t times sine of t. So now I can go ahead and integrate since I've found the dot product from a to b. Now our bounds, remember, t bounds are from 0 to 2 pi, so we just put from 0 to 2 pi, and we're going to integrate with respect to t. Now a is just a constant, so I'm going to go ahead and rewrite the integral of sine squared t cosine t dt. It's just that term first. Now once again, we can just use u substitution, so if u equals sine of t, du is going to be cosine t dt, so then dt equals du over cosine t. When I go ahead and sub that back into the integral, we get the integral of u squared cosine t times dt, which is du over cosine t. The cosines will cancel. We get the integral of u squared du, which is going to be u cubed over 3. Once again, u is sine of t, so we basically have sine cubed of t over 3. So I'm going to go ahead and rewrite that the integral is going to equal 8 times sine cubed of t over 3. And then now we can integrate negative cosine squared t sine of t. So if I go ahead and erase all of this, the integral of negative cosine squared t sine of t dt, once again u substitution, this time my u will be cosine of t, so then du equals negative sine of t dt. Then if I isolate dt, dt equals du over negative sine of t. So plugging back to the integral, we get negative u squared sine of t times dt, du over negative, not cosine, negative sine of t. Realize that negatives will cancel, the signs will cancel as well, and also we get the integral of u squared. Once again, that's going to be u cubed over 3. This time u is cosine t, so then we get a positive cosine cubed of t over 3. So I can go ahead and say sine cubed of 3 or sine cubed of t over 3 plus the integral of negative cosine squared sine, which I have found to be positive cosine cubed of t over 3. So now we can evaluate from the t bounds of 0 to 2 pi. So let me evaluate. I'll go ahead and write 8 times. Now we plug in 2 pi for t, sine of 2 pi is 0, so then 0 cubed is 0, 0 over 3 is 0, plus cosine of 2 pi is 1, 1 cubed is 1, so we get 1 over 3. Minus, when I plug in 0 for t, sine of 0 is 0, so that's 0, plus cosine of 0 is 1, so we get 1/3. So we get a positive 1/3 minus 1/3, that will cancel, and so we get 8 times 0, which is obviously just going to be 0, and that is the final answer. So now for these next set of problems, let's go ahead and use Stokes Theorem to evaluate this time the line integral along C of the dot product of f and dr. And in each case, C is oriented counterclockwise, so remember counterclockwise means positive orientation, and as viewed from above. So for number 1, we have the vector field f of x, y, z equals x plus y squared times I, plus y plus z squared times j, plus z plus x squared times k. And then C is going to be the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now notice, since we are asked to evaluate the line integral, we have to use the other formula. So we have to use the double integral described by the surface S of the dot product of the curl of f and ds. So let's go ahead and first find the curl of f. For the curl of f, we need to take the cross product of del and the vector field f. So once again, we have to create a matrix here, I, j, and k. We'll put del's components first, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then we can put f's components. So for the x component, we have x plus y squared. With the y component, y plus z squared. And then finally, that goes with k, we have z plus x squared. So let's go ahead and find the determinant. So we have I times a smaller matrix. We cross out its row and column. What we have left is partial derivative with respect to y, partial derivative with respect to z. We have y plus z squared, and then we have z plus x squared. Second term is a negative, so we have j times, cross off its row and column. What we have left is partial derivative with respect to x, partial derivative with respect to z, x plus y squared, and then z plus x squared. And then we have plus k times, we can cross off its row and column, and what we have left finally is partial derivative with respect to x, partial derivative with respect to y, x plus y squared, and then y plus z squared. So now I can go ahead and cross multiply, so we get I times, now the partial derivative with respect to y of z plus x squared is 0, minus partial derivative with respect to z of y plus z squared is 2z, minus j times partial derivative with respect to x of z plus x squared is 2x, minus partial derivative of z, or partial derivative with respect to z of x plus y squared is going to be 0, since there's no z variable, and then plus k times partial derivative with respect to x of y plus z squared is 0, since there's no x variable, and then minus partial derivative with respect to y of x plus y squared is going to be 2y. So we get negative 2z times I minus 2x times j, and then we have minus 2y times k. So that is going to be equal to the curl of f. So now that we have found the curl of f, we can go ahead and label out p, q, and r. So p is just going to be the function in front of the I vector, q is going to be the function in front of j, and r is going to be the function in front of k. And so the formula, once again, in order to evaluate this double integral, is going to be the double integral described by the region D of negative p times the partial derivative of z with respect to x minus q times the partial derivative of z with respect to y plus r times dA. So realize that we have already found p, q, and r. Now we just need to find the partial derivative of z with respect to x and the partial derivative of z with respect to y. And even before that, we need to find an equation with z equals something in terms of x and y. And in order to find what z equals, we need to look at C, which is the triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. So if I go ahead and draw that out in a three-dimensional coordinate system, so we have x, y, and z. So the first vertice is 1, 0, 0. So that's just going to be, let's say this is 1 on the x-axis, so that's going to be the point. The next one is going to be 0, 1, 0. So let's say that's 1 on the y-axis, that's the point. And then we have 0, 0, 1. So let's call that 1. So that's going to be the point. So the triangle, if I go ahead and draw it in a different color, is going to look something like this. Now we need to find an equation that describes this triangle. And this is pretty good to memorize, but the equation that describes this triangle is x plus y plus z equals 1. Because I can test any three of these endpoints. Whatever I plug in for x, y, and z, I'm always going to get 1. So if I plug in, for example, the endpoint 1, 0, 0, for x, y, and z, we'll just get 1 plus 0 plus 0, which equals 1. If I test in the other two endpoints, we'll also get 1. And if I test in anything in between, or anything in between those endpoints, we'll also get 1. Now, in order to use the formula, we need it in the form so that z equals something in terms of x and y. So if I isolate z, z equals 1 minus x minus y. So now we can go ahead and actually use that formula. So we have the double integral of negative p. So if p is going to be negative 2z, then negative p is going to be positive 2z. So 2z times the partial derivative of z with respect to x, which is negative 1. So we have 2z times negative 1. And then we have minus q. This time q is negative 2x, so minus q will be positive 2x. So plus 2x times partial derivative of z with respect to y is negative 1. And then we have minus, or plus r. This time r is negative 2y, so it's going to be minus 2y. So simplifying this formula, we have negative 2z minus 2x and then minus 2y. Now before I put the double integral, remember in a double integral we can only have two variables. So what we can do here is put the double integral in terms of x and y and get rid of z by replacing it with the z equation, which is already in terms of x and y. So I have everything inside the integral in terms of just x and y. So we have negative 2 times z, which once again is equal to 1 minus x minus y. We have minus 2x and then minus 2y. So if I go ahead and distribute over the negative 2, we get negative 2 plus 2x plus 2y minus 2x minus 2y. Realize that 2x's will cancel, 2y's will cancel, and so we're only left with negative 2. So basically we have the double integral of negative 2. Now in order to find our bounds of integration, it's going to be the same thing as the previous problem. We're going to pretend that we're on top of the triangle and we're looking basically down on the triangle to see what is the projection of this surface onto the xy plane. And an easy way to do this is to literally look at the coordinates here and eliminate the z coordinate. So we eliminate those, and so what we get is the triangle in the xy plane, or just what the triangle is on that flat plane. So if I go ahead, we graph 1, 0 first, so 1, 0, we have 0, 1, 0, 1, and then we have 0, 0. So basically this is what the triangle looks like on the xy plane. If I go ahead and draw that on the three-dimensional plane as well, this is basically the region we're looking at. Now there's a couple different ways to go about this, but the easiest way is we can say the x bounds go from 0 to 1, and the y bounds, they go from the bottom equation, which is y equals 0, or the bottom line, which is y equals 0, to the top line of the triangle, which is y equals negative x plus 1, or 1 minus x. Since the y bounds, if I go ahead and rewrite those bounds, from 0 to 1 minus x, the x bounds go from 0 to 1. Since the y bounds have the variables in them, I'm going to go ahead and put that in the inner integral. So from 0 to 1 minus x, we'll put dy on the inside and then dx on the outside, and the x bounds go from 0 to 1. So now we can go ahead and actually evaluate this integral. Now the integral of negative 2 with respect to y is negative 2y. Let's evaluate from the y bounds of 0 to 1 minus x. So we get negative 2 times, when I plug in 1 minus x for y, we get 1 minus x, minus when I plug in 0 for y, we get 0. That will cancel. I can go ahead and distribute over the negative 2 and rearrange the terms. So it's going to be positive 2x minus 2. Now I can evaluate the outer integral from this time from 0 to 1 with respect to x. So the integral of 2x is x squared, minus the integral of 2 with respect to x is 2x. We can evaluate from the x bounds of 0 to 1. So when I plug in 1, we'll get 1 squared, which is 1 minus 2. Minus, when I plug in 0 for x, we'll get 0 minus 0. Notice that will cancel. And so the final answer, 1 minus 2, is going to be negative 1. So now for number 2, we have f of x, y, z equals y times z times I plus 2xz times j plus e to the xy times k. And it's giving us that c is going to be the circle x squared plus y squared equals 16, with z being equal to 5. Now similar to the previous problem, we're still going to be evaluating the line integral along c. So if I go ahead and rewrite line integral along c of the dot product of f and dr. Now because we're trying to evaluate the line integral, we have to use the other formula, the double integral described by the surface S of the curl of f dot product with ds. So let's go ahead and first find the curl of f. So for the curl of f, once again, we need to take the cross product of del and f. So we're going to create a matrix here, I, j, and k on the top row. We'll put del's components first, partial derivative with respect to x, partial derivative with respect to y, and the partial derivative with respect to z. And then we'll put f's components, so we have y times z, we have 2xz that goes with the j, and what goes with the k is e to the xy. So now let's go ahead and find the determinant. So we have I times the smaller matrix, we cross off its row and column. What we have left is partial derivative with respect to y, partial derivative with respect to z, 2 times x times z, and e to the xy. The second term is a negative, so minus j times, we cross off its row and column. What we have left is partial derivative with respect to x, partial derivative with respect to z, y times z, and e to the xy. And then we have plus k times, we cross off its row and column. What we have left is partial derivative with respect to x, partial derivative with respect to y. Go ahead and rewrite that, partial derivative with respect to y times z, and finally 2 times x times z. So now let's go ahead and cross multiply. So we have I times the partial derivative with respect to y of e to the xy is going to be x times e to the xy, minus the partial derivative with respect to z of 2xz is going to be 2x, minus j times partial derivative with respect to x of e to the xy, this time is going to be y times e to the xy, minus the partial derivative with respect to z of y times z is just going to be y. And then we have plus k times partial derivative with respect to x of 2xz is going to be 2z, minus partial derivative with respect to y of y times z is going to be z. So we have the curl of f being equal to x e to the x times y minus 2x times I minus y times e to the x times y minus y times j, and then we have plus 2z minus z is just going to be 1z, so z times k. So now we can go ahead and actually label our p, q, and r functions. So once again, p is going to be the function in front of I, q is going to be the function in front of j, r is going to be the function in front of k. So now the next step is once again to find some equation in the form of z equals, and up here we do have z equals 5. And this is actually easier than it looks because this is the equation we're going to use. So once again, the formula in order to evaluate this double or this surface integral is going to be the double integral of negative p. So we're going to take the negative version of this, so negative x e to the xy minus 2x times the partial derivative of z with respect to x. If z equals 5, the partial derivative is 0. Minus q, so once again there's a negative in front, so it's going to be plus y times e to the xy minus y times the partial derivative of z with respect to y. Once again, it's a constant, so the partial derivative is 0 once again. And then we have plus r, which is z. So those will simplify down to 0, so we get 0 plus 0 is 0, and all we have left is z. So we have the double integral of z. Now remember that usually when we try to evaluate double integrals, we try to put everything in terms of x and y. This time we don't have to, but we know that z equals 5, so I'm going to go ahead and replace z with just the constant 5. So we have the double integral of 5. Now for our bounds of integration, we have c is the circle x squared plus y squared equals 16. Once again, since we're dealing with a circle, it's better to convert and evaluate the double integral in polar coordinates. X squared plus y squared equals 16. The center is at the origin once again. The radius is 4. Now when we convert the double integral into polar coordinates, once again we need to multiply by the extra r variable. And so for this circle, the r bounds range from 0 to 4 because that's the radius. And the theta bound, since this is a complete circle, ranges from 0 to 2 pi. So let's go ahead and just put the r bounds first. With respect to r, we're going to integrate first. And and then we're going to integrate at last with respect to theta, so from 0 to 2 pi. So now we can go ahead and evaluate. So we have the integral from 0 to 4 of 5r dr. Integral of 5r with respect to r is 5 over 2r squared. We can evaluate from the r bounds of 0 to 4. So when I plug in 4 for r, we get 5 over 2 times 4 squared is 16, minus when I plug in 0 for r, 0 squared is 0. So we get 16 minus 0 is 16. 16 times 5 is 80. 80 over 2 is 40. So now we can integrate or evaluate the outer integral, this time from 0 to 2 pi with respect to theta. Integral of 40 with respect to theta is 40 theta. We can evaluate from 0 to 2 pi. So when I plug in 2 pi for theta, we get 2 pi, minus when I plug in 0, we get 0. 2 pi minus 0 is 2 pi, and 2 pi times 40 gives us the final answer of 80 pi.